Hey guys, welcome back to chapter 16. What we're going to start to look at now is the behavior of acids. So we're going to first focus on acids because they tend to be a little bit easier, a little bit more intuitive. And then we'll look at bases and move forward from there. So first things first, strong acids. I said there's very little that you need to memorize in chemistry. I would probably memorize these 5 strong acids. So why is it important that you memorize the 5 strong acids? Well, if you know the 5 strong acids and it's not one of those 5, then you can quickly identify it as a weak acid. So just something that's super helpful to know, memorize, or just have on a note card right next to you as you're working. So strong acids in water, strong acids are 100% ions. So again, a strong acid equates to a strong electrolyte. They'll completely dissociate or break apart into ions. So the big 5 that I use the most and that I would suspect that you would memorize eventually, and you may just memorize these just by working problems. But the big 5 is hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. So those are the big 5 that you deal with the most in chemistry. Chloric and perchloric acid are also strong acids, so these would be considered strong acids. They're just not used nearly as frequently in examples and problems and quizzes. But anything on this screen is a strong acid, and if it's not on this screen, you can go ahead and assume that it's a weak acid. So here's just a clearer picture of what a strong acid looks like. So a strong acid dissolves in water. It ionizes completely. So when I put HCl into water, everything breaks apart into its ions. Nothing stays together. Here's just a picture of the molecules. So everything's an ion. Nothing stays together. Weak acids. So hydrofluoric is an example of a weak acid. So our weak acids partially dissociate in water. So here we see some of them do break apart into their ions, but a vast majority of them actually stay together. And we see the same thing in the picture over here. So break apart into ions, and then the other ones just stayed together. Okay. For the weak acids, what we're going to be looking at here is an equilibrium. Okay, so we're looking at equilibrium. So weak acids equal equilibrium. So they partially dissociate to form the H3O. Something that I didn't mention on the strong acids, but I'll go ahead and do it. We'll look at this in much more detail later. But to determine the strength of an acid or a base, what we're going to be looking at is the proton concentration. So the concentration of H plus, or remember it's used synonymously with H3O plus. So when we start to put numbers, we quantify a strong acid, we're going to be looking at the concentration of the hydrogen ions or the H3O plus ions. Same thing with a weak acid. So we're going to be focusing on this hydrogen ion or H3O ion. So weak acids partially dissociate to form that ion. So here we see the equation for hydrofluoric acid being dissolved in water. So we put hydrofluoric acid into water. The acid will donate his proton, and then water is acting as a base. It will accept that proton. Well, if this is an equilibrium reaction, right, we can write a K value. So if it's at equilibrium, in the last chapter, we called this Kc, right? Well, in this chapter, we're going to call it Ka. So the equilibrium constant for an acid. But we can do it the same way. So equilibrium constant for an acid is going to be the concentration of the products over the concentration of the reactants. So concentration of our products will look like this. And concentration of our reactants will just be HF, because remember, water is a liquid and solids and liquids do not get included, okay? So again, we see the Ka value taking shape here. So equilibrium's not going away, ice tables are not going away. So in a weak acid, we have some H3O that is created, but not very much. But if we can solve for the concentration of the H3O, then we can quantify or numerically tell someone how strong or weak this acid is. Okay. Here's our generic equation for an acid. So you'll see this in the textbook a lot. For some reason, this is something that I struggled with when I was a general chemistry student, and I find that a lot of my general chemistry students struggle with it as well. But this HA is just a generic formula for an acid, and then this A over here would be the generic anion. So it might be something like fluorine. It might be something like chlorine. So if this generic formula really just messes with your brain, replace it with something that you're familiar or comfortable with. Replace it with HF if you need to. Okay. So here we're going to see some of the skills that we learned last chapter. So if the equilibrium lies far to the right or to the product side, we'll see that the Ka value is greater than 1. And that's how we would quantitatively classify it as a strong acid. So that Ka value is greater than 1. It's going to be a strong acid. All of it's going to dissociate. If the equilibrium lies to the left, so the reactants are favored, so Ka would be less than 1, we're going to define that as a weak acid. So it's not going to completely dissociate. So as we increase the Ka, we're going to increase the strength of the acid. Or the smaller the Ka, the weaker the acid's going to be, the less it's going to dissociate. So here we see a chart with a bunch of acids and their Ka values. All of these are weak acids. And so what we see here is the Ka values. So all of these Ka values are less than 1. So that tells me that all of these acids are weak acids. And as we move down the table, they get weaker and weaker and weaker. So the weakest of the acids would be this phenol down here at the bottom. Okay. The other thing that I like to point out on this chart, so this chart's just helpful because it has the Ka values in it. So sometimes Pearson likes to do weird things to you and not give you the Ka value. They assume you're going to look it up. So some commonly used acids from this table, hydrofluoric acid used quite often, formic acid is used quite often, and acetic acid. So if you ever see those in a problem and you're like, wait, they didn't give me the Ka value, as long as they're not asking you to solve for it, Ka values are right here on this table. So it'd be helpful to come back to this as well. Okay. So let's just do a little practice. So this is actually practice from the last chapter. The second part of this will be, the first part is going to be new to this chapter. So write a balanced chemical equation for the dissociation of acetic acid and water, and then see if you can write the Ka equation. So when I say dissociation in water, your reactants are going to be acetic acid plus water, and see if you can finish that equation. So go ahead and pause the video and I'll catch up to you. All right, so let's get our reactants onto the paper. So reactants are going to be acetic acid plus water. So acetic acid is a weak acid, so we're going to have to put our double-sided arrows in there. So make sure that you're using double-sided arrows for these. Acetic acid, the name gives it away. It's an acid. So an acid does what? Proton donor or proton acceptor? Yep, acid is a proton donor. So it's going to donate this proton that's in the front of the formula. So if acetic acid is a proton donor, it's going to give that one away, and it'll be left as C2H3O2. And if it gives away a proton, it's going to be left with a negative charge. Okay. And then acetic acid is our proton donor. That must mean water is our proton acceptor. So in this case, water is going to take on that proton. So if we add a proton to H2O, it will now be H3O, and that proton carries with it a positive charge. Okay. So I was looking for the double-sided arrow and then looking for you to correctly predict the conjugate acid, conjugate base. The other thing you're going to have to start thinking about, so this one was inherently balanced, but the other thing you might have to start thinking about is if this equation is balanced. So make sure that all of the hydrogens and oxygens and carbons add up on both sides. The last thing we're going to do is write the Ka equation. So the Ka equation, remember, is the concentration of the products over the concentration of the reactants. So our products are going to be the concentration of the acetate ion times the concentration of the hydronium ion over acetic acid to begin with. So the concentration of acetic acid. And again, we don't add water because it's a liquid. So that's the Ka equation for this dissociation of acetic acid in water. Hope you guys found this helpful.